Hey there, YouTube. So today we're going to deconstruct coefficient alpha. And what I mean by that is we're going to take a look at the three elemental components of your alpha statistic. Hopefully, this deconstructive focus will help you better understand what alpha is really reflecting when you consult this very common index. So, alpha is an estimate of internal consistency, which is almost always computed and reported when dealing with multi item scales. You'll want at least three items in order to compute a meaningful alpha, and those items all need to be indicators of the same construct. Procedurally, we look for internal consistency by evaluating similarity of response across our multiple items. If one respondent strongly agrees that he loves to be around people, then the expectation is that he'll also agree that he doesn't like to be alone, because both of these items are proposed to be indicators of the same construct. In this case, a sociability saturated construct, something like extroversion, perhaps. Now, we want to quantify this consistency. So, of course, we turn to statistics for a procedural specification. And the statistic that we use to imperfectly estimate consistency is the covariance. Here are some example covariances, which can look a little scary. But if you're familiar with a correlation, or even better yet, a correlation matrix, that's exactly the same thing that you're looking at here. The only difference is that you probably expect to see the number 1 in the diagonal of a matrix like this. We actually get those values of 1 if we standardize our item responses prior to estimating the covariances. But for the purposes of alpha, we don't need to do this extra step. We can just analyze the raw item responses. In our example here, we have 6 items, and the full crossing of how all these items associate with each other is presented in this matrix with 36 values. The values in the diagonal are kind of unique, so we don't need to do this, but we can give them a name of their own. And if we do that, we call these variances. And this entire matrix of 36 values is sometimes referred to as a variance covariance matrix. Now, these numbers in the diagonal are the same variances that you would get if you applied the standard variance formula. It just looks a little more complex here because there's 6 of them. The off diagonal elements in this matrix are what most people refer to when they talk about covariances. These reflect the association between all of our 6 items. For example, the covariance between item 1 and item 3 is 0.23. We don't know if this is a strong or weak association because, unlike the better known correlation, the covariance is unbound. Its values are impacted not only by the magnitude of association between the variables, but also by the scale of measurement of those variables. We don't really need our eyes to tell us if a covariance is large or not, because what the procedural index really wants to know is how much covariance is there relative to item variance. So coefficient alpha is fundamentally a ratio of how much do people differ in their responses within items to how much association is there between item responses. The ratio on the right here is what alpha is really trying to get at. The other stuff's just getting the ratio on a meaningful scale, such that numbers closer to 1 reflect more consistency, and also making a bit of a misguided correction based on how many items we have. Now, this item correction acknowledges that there's a bit of a problem with the number of components in our variance covariance ratio there on the right. We'll be coming back to this, but let's focus on the fundamental components right now. The covariance elements of our alpha formula are the 30 numbers in red here. Although humans don't typically do this, alpha does need to look at the association between item 1 and item 2, as well as the association between item 2 and item 1, even though they're going to be the same value. The variance elements are our 6 item variance estimates in the diagonal. To get alpha, you can literally just add up the numbers in a variance covariance matrix like this one, apply the adjustments to the left, and then spit out a number, which we refer to as coefficient alpha. Okay, so let's open up a computer program and deconstruct alpha. We'll apply the conceptual formula and see if we can match the computer's estimate, which uses a different computational algorithm. So I have 2 small demonstrative data sets here. Both of them are derivative of a larger personality assessment. What I've done is I've taken one of the scales on that assessment and made it even smaller. So these are normally 12 item scales. I have a data file with 4 items in a subset of the 12. These are neuroticism items that are taken from an instrument known as the NEO, which is an acronym for neuroticism, extroversion, openness. It's actually a 5-factor model personality inventory that's fairly popular. Let's go ahead and annotate what we're doing here. And I'm going to read in my small data set. Let's take a look at that small data set. And there are 4 items represented. They have non-sequential names because, again, they're taken from a much larger data set. I wanted to have a smaller data set that wasn't as intimidating. So let's go ahead and ask for our variance covariance matrix. Here it is. There are 4 items represented, 4 columns, 4 rows. Again, the covariance matrix, many are more familiar with the correlation matrix. And so we'll take a look at that in comparison. And you see a distinction here primarily in the diagonal. Okay, so what I'm going to do with this covariance matrix is I want to break it up. Now, if we take a careful look at that conceptual formula for alpha, you're actually going to see that the denominator is this entire matrix. It says the sum of the variances plus the covariances, but that's everything. So really, all we really need to do is isolate the diagonal. And so I'm going to save the covariance matrix as an object. Let's call it small cov for small covariance matrix. If we had missing data, which we don't, we'd want to do a qualifier here, and that is to actually parallel the way that the alpha analysis uses missing data. The default in most psychological applications is to retain pairwise comparisons. And so we're going to specify that here. It's not necessary because we don't have any missing data. It won't hurt anything. If I look at my small cove object, it's the same as it was before. We're actually going to save the diagonal of that. And the way that I'm going to do that is I'm actually just going to ask for rows and columns that are the same. Let's see what that looks like. So we'll ask for our diag object. And I see that it is the elements within the diagonal, just to confirm, 1.28, 1.5, 0.93. So consulting our conceptual formula, I have variances in the numerator and I have everything in the denominator. So let's try to get those values. If I ask for the sum of my diag object, I see it a 4.63. If I ask for the sum of my entire matrix, I see a 9.78. So let's go ahead and divide those values. See, let's store that object. So this is my ratio. And so I want to reflect that ratio. And by reflecting it, I just get it on a scale where higher numbers are more desirable. And so you have 0.52666703. The final adjustment I'm going to make is based on the length of the scale. Now, I've mentioned this is a bit of a misguided correction, and the reason for that is the problem is large item scales have an estimate that's too high. The correction is giving a bump to low item scales. So it's not a great correction, but it's a correction with good intent. So we have 4 items, that's our K. So the formula is K over K minus 1, that's 4 over 3. So that's a 1.333 repeating. Go ahead and multiply that by our 0.5266703. And that's actually, save this as our alpha guess. We don't need to look at that value yet. We'll go ahead and load in psych package and ask for an alpha on our small object. And I see that I get an alpha of 0.7. Let's take a look at our alpha guess and see what that was. Yeah, 0.7. So there's an additional piece of information that you have here that's a little bit different, and that's your standardized alpha. Standardized alpha is not frequently used in psychological assessment because it's intended for situations where your indicators have different response scales. The standard convention in psychological assessment is to retain the same response scale across indicators. So this isn't an index that we would typically consult or report, but it's simply alpha computed from standardized scores instead of raw scores. So we can actually standardize our scores, and that means give them z values. So we're actually going to a new object, we can call it z small, and we'll have R do it automatically for us. We'll just ask for z values in that object. If I want to confirm that these in fact are z-scores, I can do a descriptive on this. And my expectation is within rounding, my item means and standard deviations should universally be essentially 0 and essentially 1. And here I do have zeros and ones. So if I apply alpha to this data set, my expectation is the standard alpha is going to be 0.71. It's going to be what the standardized alpha was with my raw data. So there we have it. I'm not going to confirm this one with the application of our conceptual formula because this video is going to run too long if I do that.
Okay, I actually chopped the second walkthrough with the messy data because the video went way beyond my 10-minute goal. The point of this is to highlight the three elemental components of alpha: the covariance, the variance, and the number of items. It's important to understand what alpha is actually a function of so you don't misinterpret the consequences of a good or bad alpha. Especially keep in mind that left-hand item correction. Probably have a future video that further explores alpha's vulnerability to large item scales, but for now I think we'll call it a day. Thanks for watching. Let me know if you have any questions or ideas for future videos, and happy psychometric.